In the previous video lectures of this unit, we saw law of large numbers, and we saw how different modes of convergence relate to each other. And there's one of those modes that we have not yet mentioned yet, which is convergence and distribution. We have seen that convergence in probability, when measured, convergence in probability is the weakest one for a probability space, in the sense that it is implied by convergence in LP or convergence in almost sure. And now we're going to see that convergence in distribution is the weakest of all forms of convergence of random variables. So let's start by showing that convergence in probability will imply convergence and distribution. So this is exactly what this proposition here is saying. It's saying we have a probability space and a sequence of random variables on that probability space that converge in probability to another random variable. And in that case, this sequence of random variables also converge to the same random variable in distribution. So before we prove this proposition, let us move forward here and see what we are proving. So this proposition is saying convergence in probability implies convergence in distribution. So this, finally here, this is the complete diagram of which type of convergence can imply other types of convergence. So we know on probability spaces, not on measure spaces, on probability spaces, almost sure convergence implies convergence in probability. We saw this 2 video lectures before. We also saw in the previous video lecture that convergence in LP implies convergence in probability. We also saw that if we increase P, convergence in LP plus something implies convergence in LP. We also saw that, well, convergence in probability will imply convergence in LP in case the sequence of random variables is dominated by one random variable in LP. And we have seen that the sequence of random variables that converge in probability has a subsequence that converges almost surely. That is true in general for measure spaces. If there is convergence in measure, there will be a subsequence that converges almost everywhere. So again, what we're doing in this video lecture, we're showing that convergence in probability implies convergence in distribution. Of course, convergence in distribution cannot imply any other. It cannot imply convergence in probability, and you can just think of some very simple example of why convergence in distribution cannot imply convergence in probability. And because it cannot imply convergence in probability, it cannot imply any other, because the others do imply convergence in probability. So this is the theorem, the proposition we have just stated is this implication here. And the second proposition is this one. It says, if a sequence of random variables converges in distribution to a random variable x, which is a constant random variable, so x is equal c almost surely, then in fact this sequence of random variables converge to that constant in probability as well. So this will be one particular case, which is here, this dotted line here, which is a particular case. So convergence in distribution does imply convergence in probability in this particular case when the limiting in distribution is x equals c almost surely, which means if we plot y equal fx of x, we have its distribution function is a very boring one. It looks like this. It's a random variable that's not very random. So in that case, convergence in distribution will imply convergence in probability. So to complete this diagram, we have all these, this part of the diagram that we have proved already in the 2 previous video lectures. And to complete it, we're going to show now these 2 arrows here. One proposition is convergence in probability implies convergence in distribution, and the other will be convergence in distribution to a constant limit implies convergence in probability to that constant. So we start with the proof of the second proposition, We know that convergence in probability in distribution does not imply convergence in probability in general, but we're going to show that in case the limiting distribution is a degenerate and puts all the mass on the same number C, then there is convergence in probability. And the proof is rather simple. So if xn converges in distribution to x, where x is almost surely equal to a constant, that means the distribution function of x is a function that just takes two values, 0 and 1. There is a number c where it jumps from 0 to 1. And what does it mean to say a sequence of random variables converge in distribution to this? Well, it means for any number different from c, if it's to the right of c, then this is a point of continuity of fx. So this is y equal fx. Any number larger than that, this distribution function converges to 1. Any number smaller than that, this distribution function has to converge to 0. Which distribution function? Fxn of x has to converge as n tends to infinity. It will converge to 0 if x is less than the constant. It will converge to 1 if x is more than this constant. And convergence in distribution doesn't say anything about what happens for this value of x exactly equal to c, but it does not really matter. So this is what is written here. Fnx converges to 1 for x larger than c and converges to 0 for f smaller than c. And now we have to show convergence in probability. As we know, convergence in probability means we have to look at this difference, look what is the measure or the probability of the set where this difference is larger than epsilon, and show that it converges to 0 as n tends to infinity. Well, first, let's bound this from above. If this distance is larger than epsilon, it means either xn is less than c minus epsilon, or xn is more than c plus epsilon. So we can write this as since these two are disjoint events, we can write the sum here. And the only reason why this inequality here is an inequality and not an equality is because we are writing here less than or equal to instead of less than. Now we can write exactly what these two terms are. What is probability that fn, or what is the probability that xn is below a certain value? This will be the distribution function of xn evaluated at that value. And what is the probability that xn is larger than a certain value? It will be 1 minus the distribution function evaluated at that value. But because of what we have just discussed here, of this convergence before and after the point C, the first one converges to 0, the second one converges to 1, and we have this 1 plus 1 minus here that stays. So we see that this converges to 0, which is what we had to prove. So this proves that xn converges in probability to C as claimed.